Hi, this is Larry Benko, W0QE again, and this is the 8th video in the SimSmith Basics series. This video discusses ganged and custom components. As we become more proficient with SimSmith, we try to use SimSmith to analyze more complicated circuits and circuits which generally are not as well known. These circuits often have components which are not part of the SimSmith repertoire of components, which is shown down here in the lower left. These components represent, well, some of these don't represent that common of a component, like this one, and even perhaps the transformer, but these others are very common components. However, there's a lot of components in electronics that we have that are not represented by the group that SimSmith provides naturally. However, SimSmith does provide us a mechanism to create these components quite easily and use exactly the component that we wish to have. A good example of that would be gang capacitors. Two capacitors mounted on the same shaft are a gang capacitor. When one changes in value, the other changes in value. The capacitors do not need to be aligned. They don't need to be the same value. Doesn't matter. As long as you mathematically can say one value changes relative to the other value at a certain amount or a certain way, you can do build the component just fine. Ganged inductors. You see this component sometimes in balance tuners. Differential capacitors. Johnson Matchbox had those. There was a group of tuners in the 70s and 80s called the SPC tuner and the ultimate TransMatch, which were variations on the T network, which had a differential capacitor in them. The differential capacitor is fundamentally two capacitors where one goes up in value while the other one goes down in value. Sometimes it's actually built as two separate capacitors. Sometimes it's built as a common rotor within two stators, but nevertheless it still performs the same function. Potentiometers, not necessarily very useful for tuning or matching, because they're the loss represented in a component like that. But there's a lot of other electronic and RF circuits that a potentiometer is very useful for. Relays or switches. This is a big deal. Very, very few tuners that you might want to analyze or circuits you build will not have a switch or a tuner in it somehow to add or change the circuitry somewhat to increase its matching range. Attenuators. Just like you buy an RF 3 dB attenuator, you can build those in SimSmith. Multiple coupled coils. Many Smith chart programs do not have the ability to support 4 or 5 or 10 coils that are all coupled together with various degrees of coefficient of coupling. SimSmith does this very nicely. Precise components. We've touched on this in the past, but don't underestimate the ability to analyze a component very, very accurately by measuring it with a little network analyzer. Components like ferrite beads and stuff like that are almost impossible to mathematically come up with a formula for them. Just measuring them is a lot easier and more precise. And while we're on that topic, balance. There's a lot of different balance types that SimSmith can analyze very, very well. I might mention at this point that one of the components that we can't easily do is trifilar, quadfilar type windings in balance and stuff like that. I don't know of any way to do that at the moment. Perhaps sometime in the future there will be a way to do that. But this group of components here really gives us a large group of things that we can now include in the gamut of circuits that SimSmith is capable of analyzing. We will see this funny looking construct appear very often in the circuits that I'm going to build here today. This construct is not really well advertised in SimSmith. It does exist. It exists in the F block, the N block, and the ruse block, and it's almost exactly an if statement. It has two forms. They're really the same, but it performs. We can perform a test. We can say, like, is the capacitance greater than 50 picofarads? If the answer to that is true, we do something. If the answer to that is false, we do something. And the something we do is a returned value. And I'll explain this a little bit more in a minute. We also do not have to do a test here. This can be just a number. So if the number is non-zero, which is the same as true, we do the same thing as up here. If the number is 0, we do the false case. So let's look at a real simple example here. RA is the value of a resistor. And we have another variable called mode. So we can say RA is equal to the result of this function. And this function, mode, if mode is not equal to 0, we return 50 ohms. If mode is equal to 0, we return 75 ohms. So this resistor that we're going to set with value RA will basically be 50 ohms when mode is not equal to 0, and it'll be 75 ohms when mode is set to 0. So that's a very simple way to change a component based on a variable. And you could change any component. It doesn't have to be a resistor, of course. Here's a case where we have a dial, say. The dial runs 0 to 100, and that's all we want it to do. And 0 to 100 gives us the minimum and the maximum of something. I don't care again what it is, but it's just the limit. So here I can say, we'll call this value percent now because it's going from 0 to 100. If percent is greater than 100, then we're going to return 100. Otherwise, we return just the value percent. So what happens to percent here? If we're scrolling our mouse wheel and moving it up and down in value, if at any time it gets greater than 100, we jam it back to 100 right away. Similarly, on the downside, if it ever goes below 0 here, we jam it to 0. Otherwise, we return its current value. We can combine these two commands into one command, and I use this command all the time. It has I put different things in the spots here, but it does exactly the same thing. Here's a case where we say the value this function returns if percent is greater than 100 is 100. So it stops at 100 on the top side. If it's not greater than 100, then we do the function again. We say, is it less than 0? If it's less than 0, we return 0 into this spot, which then returns that back to here, or we would just return the value itself. So this is a true limit switch. Stops at 100, stops at 0. Here's a case where we put a resistor in a circuit, and we're going to call the resistor a relay contact. If the mode variable is true, think of that as the relay energized. We're going to set the contact resistance to 1 microohm. If the mode is equal to 0, we're going to think of that as the relay being released, and the contact is 1 gigohm. This is a pretty ideal relay. In RF world, we can do this a little bit differently and get a much more accurate contact. We can say if the relay is operated, again, mode is not equal to 0, then we're going to provide an inductance in place of the contact. In this case, it's going to be 30 nanohenries. Omega is 2 pi f at the current frequency we're using, and 30 nanohenries. So 30 nanohenries represents the relay contact and a little bit of wire. And it's a pretty typical value. It might even be a little bit more than that based on how you've wired it up. Likewise, if the relay is off, we're going to let the contact look like 3 picofarads. A negative capacitive reactance, or capacitive reactance, which is a negative value, and so it's the reactance of capacitors 1 over 2 pi Fc. So here we go, or J over 2 pi Fc. So this is omega is 2 pi f, and this is the C, and they're both in the denominator. So these constructs really give us a very nice set of tools to vary things. Now I can go through a real quick example of that. Let's leave this off to the side just briefly and cover this up. This chart doesn't really mean anything. I'll do this for the moment in an N block. It really doesn't matter where I do it. We'll click on the N block, and we'll basically set a variable to be. We'll give a variable a name, and let's call this our dial. And I just put it there to force us to have a value here. Now, we can hard code this or we can soft code it. So in this case, let's soft code it. So we're going to say, let's call it D max for dial max. And we're going to say the dial max equals, say, 20. And we're going to say the dial minimum equals 5. And then we have a value called dial. And this is some knob or something else. It doesn't really matter what it is. Now here's where it gets interesting. And now we can say dial equals, and we ask the question, dial greater than D max. And if we get that to be the case, then we set the dial to just to be D max. Otherwise, we'll return dial. Now, if we run this, what we will see is dial can, let me make this be integer values just to show it easily. As we crank this up and we get to 20 and see we stop at 20. It can't go any further than 20. It tries to go to 21 and immediately it gets set back to 20. So now let's go back and add one more line here. We'll take this line, copy it. We'll use it again, except this time we'll say less than the dial minimum value. If that's the case, we put dial min in here, and we run this command and then this command in order. Now we will go up here. We still stop at 20 on the top end. We go down, and we stop at 5 on the bottom end. We try to set it to 4, but we can't. He keeps getting pushed back to 5. And to finish this up, we will take this part of the command right here, and we'll do what we did before up here, as we will put it in this command. Running out of space here. And we have an error now. Let's see. Dial greater than D max, we return D max. There we go. Okay, so here it is again. If the dial is greater, if the dial value is greater than the maximum value, we return the maximum. Otherwise, we do this if we fail. So if we fail, we have 2 more tests to do. If it's less than the minimum, we return the minimum. Otherwise, we just return the value. So let's run this and see what it looks like. We get up to 20, it stops. We get down to 5, it stops. One line, and now you can't get out of control. You can only set the values as allowed. Now we set these values. We set and initialize these values. We didn't need to initialize these values. We could easily have just made a variable here and a variable here, been done, and you could have done what you wanted to here. Let's set this now back to 10, say. Let's set this to be 6. And we'll run this again. Well, as soon as I click on anything, it moved this to 6 because 6 and 10 weren't within the limits. There we go. I didn't mean 6 and 10 weren't within the limits. I meant the dial was not within the limits of 6 to 10. Here now it's 6 to 10. These become inputs. If you want to, you could also have hard-coded them in here too. It wouldn't have mattered. All these are perfectly legitimate ways to do this kind of a function. And this function is an extremely important function when you're just fooling around and you want to keep stuff under control. All right, now let's get rid of this. Get rid of that. Let's just get rid of everything here. In the, 70s or 80s, when the T-tuner became really popular as a device to match networks, there were a lot of people who didn't like the fact that the T-tuner, which is a high-pass configuration, this particular T-tuner does a very nice job over the HF range with reasonable valued components. That was its claim to fame. El networks, the inductance would get very, very large or very, very small in some cases. The capacitance could become huge. To match a 20-to-1 SWR on 160 meters, the capacitance could be as large as 8,000 picofarads. This network matched a lot of those impedances very, very nicely, did it fairly efficiently, not as efficiently as an L network, but it did it fairly efficiently, and it was easier to produce. However, it had no harmonic suppression in it. It's a high-pass network. The harmonics of the transmitter go right through it. So there were some bright ideas that came around. And the first idea, I don't know who beats who in terms of time, but there were two variations on the T network that came about. I'm going to call the first one here where we put this will become a differential capacitor. I'm going to put this differential capacitor at the generator. If I put this differential capacitor at the generator, this was the tuner known as the ultimate TransMatch. And it was a brainchild of W1ICP, Lou McCoy. He wrote a bunch of books in that era. And they touted all kinds of good things it could do, but nevertheless, it was fundamentally a T-tuner, and this capacitor C3 was to give you some harmonic suppression. So now we need to control this as a variable component. So let's put a network back in here again. And while I'm at it, I might mention the fact that these three lines are needed in the in-network, in-block. If you don't wish to do anything in the block and you want it just to look like it's a through, RF-wise, and you want to do all your control, you want to control something in some components here within the in-block. These components, by the way, have no provision to put any programmability in the component. They have a value, they have a Q, and the Q at a frequency. You cannot put a command that says C2 equals something. You have to put that somewhere else. We put that in an F block, an N block, or a ruse block. I'm using an N block for the moment. So the first thing we're going to do is we're going to come up with something we're going to name this function. We'll call it differential capacitor. And we're going to come up with a variable called Cmax. I'm going to set that to be 400 picofarads. We're going to have a variable called Cmin. I'm going to set that to be 30 picofarads. And I'm going to have a variable called Cdiff. That's a differential capacitance that I want to set this capacitor to, and it'll be the value of C2, and then C3 will track C2. So that's the first thing I do. Then I come down here and I set, I'll say C2 dot F. That is this value right here, C2 F, and that's going to equal to my local value, my local variable Cdiff. Then C3 F, which is the other side of the differential capacitor, is going to equal Cmax plus Cmin minus Cdiff. Okay, let's see how well we did here. So here's where I set my value. So let me just set my value to be 30 picofarads. If I set this one to be 30, it sets this one. Now notice I can no longer set this component. I can no longer set this component. These components are not settable any longer for the very simple reason that they continue to be overwritten by this one. However, if I set this to be 30 here, this is 400. That's exactly what we asked for in our capacitor. If we bump this one, let me set this to be arithmetic, say values of maybe, I don't know, values of 10, say 10 picofarads. If I bump this up by 1, we will notice that this went to 40 and 390. We bump it up again, 50, 380. and we bump it all the way up. Eventually, we're going to bump it up to the point where $430. So it runs through the gamut. However, if I continue to go, I'll go and I get negative capacitances on this side because that's how the math works. And if I go on the downside, I'll get, again, negative capacitances down here. All things we don't want to have. So back again to this formula, and let's add one more little piece of information to it. And that's the command where we look at the values. So what we're going to do is we're going to say C diff is equal to, and we're going to do our first test. C diff is greater than C max. So if that's true, we would perform the value here. So if this is true, we're going to do this. The first thing we're going to do is we're going to set the value of C diff to be equal to C max. We're not going to let it ever get above C max. Likewise, if it's less than, this isn't greater than, it's less than or equal to, we're going to do what's in this group, what's in this parentheses. The first thing we're going to do here is we're going to ask the question C diff less than C min. If the answer to that is true, what we will do is we will return C min. Otherwise, we're just going to return C diff. Now, I'm doing this on the fly, so there's very possible I can make mistakes. So let's return this and see what happens. Here we're at 30. We try to go below 30, it won't go. It goes up, stops at 30 on the bottom downside, 30 and 400. We're going to go the other direction. We get up to 400, it stops at 430. So we've built our differential capacitor. Now this is our tuner. Let's see if we can match 200 plus J0 to 50 with this circuit. And let's see here. This is, now what I'm doing right now is easy to do if you've got enough experience with messing with this stuff. It kind of becomes like second nature. One thing that's a downside, if I had done all of this inside an N block or inside a ruse block or inside an F block, I would have had a straight line that went from here to the result. And that does not let me see what's going on. So sometimes it's nice to be able to see. Sometimes once you understand it, it's nice to put it all in one block. And if you put it all in one block, then it gives you more room for other components and stuff. But let's... I'm getting close here. Let's call that good enough. So this is the ultimate TransMatch done at 14.1 megahertz, matching 200 ohms to 50 ohms. A little while later, Doug DeMaw, W1FB, came out with a variant of this thing, and the variant was, we'll put the differential capacitor on the antenna side. So let's just do that. We don't need to do anything else in the circuit other than drag this component over here, drag this component over here, drag this component over here. We're done. Exactly the same thing we had before. We can still control these two components. See that both of the differential capacitor controlling both of those values. Still the same value here, same value here. Now let's see if we can match that circuit here. All right. Okay, let me get going here. Let's see. This is going to be easy to match, I think. And this is not necessarily the most efficient match by any means. It's just a match. There we go. Good, bad, whatever, I don't know. It's a match. So this again is another circuit. But our differential capacitor here was easy to implement. If we want to tune stuff, I have to go over here and over here to tune these two components. I go down here to tune these two components. I don't have to do that. I could easily over here say L1.H is equal to my own variable L1. And let me put these, by putting these up here ahead of time, I can control the order in which they appear. The order in which they appear is kind of nice because then, oops, I don't have to worry about what I'm going to have here is these three are going to be adjustable. These are not adjustable values. They are values that are just there for information. So I can say L1.H equals L1, and I can say C1.F is equal to C1. And of course, when I do this, my circuit's going to be drastically different because these two values went to 0 because these were 0 when they came in. This is about 750 nanohenries if I remember correctly. Yeah, it's pretty close. And then this was 300 picofarads maybe. No way, that's way too much. Okay, we'll get there. Okay, everything in this tuner, all three controls are put right here, here, and here. There's the controls. Up here, I cannot control this anymore. I cannot control this anymore. And I cannot control the differential capacitor. Very simple. You know, stop the video at any point in time and to look at this stuff and spend time understanding it. But this is an extremely simple way of being able to build a component that is not normally in SimSmith and use it as you wish. To save some time, I've built this circuit in advance. I know building these circuits up as we go along in the video might be more instructive. It unfortunately takes a lot longer time. So I built a potentiometer here as an example. And here's the potentiometer. I built two potentiometers. One a combined control and ruse block at the same time, and one where the ruse block was just the circuit and the in block controlled it. And I'll show both of them. They both do exactly the same thing. But here's the first case where we have the ruse block does nothing more than it's two resistors. This is the potentiometer. Think of this point right here as the wiper. We have a circuit which provides, shrink out a little bit. We have a circuit which provides a 10-volt generator. We have a isolation block which clones the generator and the load. So it's a 10-volt generator here, 1 gigohm load here, 1 gigohm load here. It's just an open circuit potentiometer. We're going to look at the wiper voltage. So we do exactly what we did before with the differential capacitor. This time I have this stuff on top. It doesn't really matter. I declared two variables, a total and a K. K is our fraction of the way up the wiper, fraction of our way up the wiper. 100 ohm total resistance for the resistor. And basically what we've got here is in this block, we're going to show the values of these resistors. So if I set this thing down to 0, we're at the bottom of the wiper. We have the bottom being 0, the top's 100 ohms. As I turn my dial up 10% of the way, the bottom is 10 ohms, the top one is 90 ohms. 20, 30, 40, 50, 60, 70, 80, 90, and all the way up to 100%. If we look at the voltages on the output, we see 10 volts when it's at 100%. We see 7 volts when it's at 70% or 0.7 of the way, 5 volts at 0.5 of the way. So this performs a potentiometer function very nicely. It stops at 0, it stops at 1, which is exactly what we want. We've done that with, let me get rid of some of these. These are extra commands I had in there. This is an incorrect statement here. Okay, this is the same function again. There we go. So what we do here, though, to control the actual value of the components, we refer to this device, this component, as U1. That's its name. U1 dot R bottom and dot R top are the variables that I control. The top of the resistor, or excuse me, the bottom resistor is K, which is the fraction of the way up the potentiometer the wiper is, times the total resistance. The top is 1 minus K, which is the residual of what's left over after we take K away from on the bottom. And that's all there is to it. So again, the resistances go just like a regular potentiometer goes. And this is a very nice, simple potentiometer. If we look at the combined circuit here, it's very similar again to the other one, except it does not need to do the referencing to a different component. It's itself, so U2 doesn't become part of it. So we have a total, a top, a bottom, and a fraction of our way up. The total can be set here. The top and the bottom are calculated values, and here's the percent of the way up. We have 3 volts out. We 30 and 70 ohms. As we move this down, we see our potentiometer moving just like it normally would. You would expect it to move. This is having done the same circuit in a single block. Now, why would we want to do it here rather than in a single block? Well, there's several reasons you might want to. By doing it in a single block, it's all self-contained. However, if I had other stuff going on in the block, I might end up with a lot of parameters here. A lot of the parameters might not be parameters you want to adjust. You want to adjust just some of the parameters. Putting the adjustable parameters in some other block has the beauty of being able to say, these are the only things I adjust in my circuit. I could call these adjustable parameters to kind of remind you that don't mess with these. These are like the default starting parameters. Or, I mean, a good example would be if I was going to build a T network and I had a whole bunch of 250 picofarad capacitors, but then I found some 500 picofarad capacitors. That sets my maximum value. So I could set my maximum capacitance values here, and I'd still be able to control them from the minimum to the maximum values over here. It's just a matter of convenience how we do this kind of stuff. But there's a ton of different ways to do these things, and I've only touched on just a few of them. But hopefully these are some examples, and there's some good ideas that people will get from it and understand how flexible SimSmith actually is. All right, one final example here. Here's an example of a relay contact done in a ruse block. There are no variables other than a switch, whether it's on or off for the relay. Everything is done inside. I've declared the relay contact. This is the contact. Think of this as a relay contact. I've used this function here. This is the same function we've been using all along. I can't make it any larger in here, but it basically says we look at the switch SW for whether the switch is on or off. If it's on, we set it to 20 nanohenry inductance. If it's off, we set it to 2 picofarad capacitance. Whether this is realistic or not, you would have to determine in your circuit, but these are pretty good values. A contact of on is 20 nanohenries and off of 2 picofarads is pretty good. So let's look at what we get in a 50 ohm circuit here. If the circuit's open, our impedance is no longer infinity. Our impedance out here it's a big value in parallel with 1.999 picofarads, it should be this one here. It's 50 ohms in series of 2 picofarads, which is exactly what this circuit is, 50 ohms and 2 picofarads here. Likewise, if I operate the relay, when I operate the relay, it's a non-zero value. The relay's released at 0. So any negative values, big positive values, it doesn't matter. I didn't put any limits in this circuit. It's just 0 is off, any other number is on. Here's a case when it's on, it's not a 1-to-1 SWR anymore. It's basically 50 ohms in series of 20 nanohenries. And that's the resultant SWR of 1.074 at 28.5 megahertz. That's why it's important when you put circuits, switches, relays, and stuff in a circuit that you understand what they're going to do to the circuit. Of course, a circuit like this could be somewhat compensated for by a small capacitance to give you better on SWR characteristics, like right there. But of course, when we turn it off, we have to worry about what the capacitance does when we turn the relay off. But people do this all the time. You typically have excess inductance in circuits, and you add small shunt capacitors to fix it. One final example before I'm done with this video, and let's look at this. This is a switchable L network done with, again, with relay contacts here. I used basically ideal contacts here, a gig ohm when they're off, 0 ohms when they're on. 0 ohms can often be problematic if you're not careful where you put it in a circuit. 1 micro ohm can save you sometimes. But in this case, there's impedance in the circuit, so 0 ohm resistors don't hurt us. We have a basically an L network that we can switch the capacitor either to the antenna side or the generator side. And you notice that when this contact is 0 ohms, when the switch is a true value, it's 0 ohms. When the switch is a true value here, it's 1 gig ohm. So this is a complementary contact. This is a this contact right here, whenever the switch is on, basically the contact is made this way and this one's open. Likewise, when the relay's off, this one's made on and this one's open. So we can switch back and forth. And then what I'm also doing at the same time here is I'm sweeping the component values. So I'm saying that the inductor here runs from 200 nanohenries to 10 microhenries. I'm doing the circuit backwards because I want to look at the matching range. We've discussed that before. So I start with my generator over here. I basically put my circuit here in reverse. I make my component values negative. My capacitor runs from 30 picofarads to 600 picofarads, and here's the value I get. Now watch what happens as I change the circuit. So I change the circuit, and there's the other circuit. So as we've been told many, many times in the past, a given L network can only match a certain range in the Smith chart. This one matches approximately half the Smith chart. I didn't make the values large enough or anything else to make this, be a real good network. But this shows us the other network, and it matches some of this range. It doesn't match it well enough. If we go out here to the outside edge, we can see that basically we're at 600 picofarads. Well, geez, we need more capacitance than 600 picofarads to match that. So we can come down here and make this number larger. Let me close this off. It's not needed, really. So now we're going to say on 10 megahertz, we got to get all the way to basically, let's say we got to get to 2,000 picofarads. And then up here, what's the problem? The problem up here is at 200 nanohenries. Well, that's a little bit of a problem. It's hard to get the inductance to be just arbitrarily low, but let's assume we were really, really good and we have a really, really good inductor and we can get it down to, say, 40 nanohenries. So that's the range that circuit would work over. And here's the range the other circuit works over. This circuit doesn't make it all the way for the very simple reason that we're 30 picofarads from the minimum capacitance. And this is the problem with the basic L network in general. You end up with component values that end up being incredibly tiny. Good luck coming up with a capacitor that's going to go to 600 picofarads, or no, excuse me, go to 2,000 picofarads and have 8 picofarads as a minimum value. That just is not going to happen. And likewise, in this case, we have an inductor here that is 39 nanohenries and needs to go all the way up to, well, I never really, let's see how, can we get away with less inductance? All we're losing is this little tail at the end here with inductance, so we don't need a 10 microhenry inductor on this side. And on this side here, what happens if we have less inductance? We lose a little bit on the outside. So we do need 7 or 8 microhenries if we want to match this really well. But nevertheless, this was not a matching example. It's more a configuration example to show you how you can use the relay switch to basically toggle the two networks. And you could make the complexity of this circuit as much as you wanted to. This could be very easily, could be bands. These could be a band switch that would go across shorted sections of inductors. The inductors could be coupled together. I didn't talk about that in this video either, but you could couple the inductors. You could see the voltage across the switch contacts in a band switch. There's some incredibly powerful things you can do in SimSmith. Those topics are probably outside of the realm of being in the basics, but if you learn the basics, pretty soon you'll be experimenting with more complicated things. And there's really a lot of really, really valuable stuff you can learn with SimSmith doing these additional components. So I hope everyone's enjoyed this video, and as usual, there'll be more.